Welcome to this explainer. If you've been following the rapid evolution of large language models, you already know they're incredibly powerful. But up until now, we've mostly treated an AI's ability to think and its ability to do as two completely separate tracks. Today, we're unpacking a really fascinating piece of research called ReACT that proposes a fundamental upgrade. It asks a pretty profound question. What if we gave AI an inner voice to think with and a set of hands to interact with the world at the exact same time?
So before we get into the weeds of neural network architectures, let's just ground this in reality for a second. Think about this. How do you cook a dish in your kitchen? You don't just blindly chop vegetables for an hour with zero plan, right? Nor do you just stand there perfectly still, deep in thought about a recipe, without ever picking up a knife. You naturally and seamlessly combine thinking and doing.
And that perfectly illustrates human cognition. Our brains are constantly alternating between inner speech and task-oriented actions. You reason, okay, now that everything is cut, I should heat up the pot. Then you act, you turn on the stove. And if you hit an unexpected snag, like realizing you're totally out of salt, your reasoning steps right in to handle the exception. You think, I'll just use soy sauce instead. Then you act by opening the fridge. This tight, continuous synergy is exactly what allows us to learn quickly and make robust decisions when things get uncertain.
Now contrast that human approach with how AI has historically been built. It turns out we currently have two dominant but totally isolated paradigms. On one side, we've got reason-only AI. Think of chain of thought prompting, where models produce these brilliant step-by-step reasoning traces but never actually interact with the outside world. On the other side, we have act-only AI. These are interactive models designed to navigate websites or simulated environments, predicting the next action based on text, but without ever really pausing to explicitly reason about their high-level goals.
The crucial point here is that both of these isolated approaches have fatal flaws. A reason-only model is basically like a master chef who plans an intricate, 5-course meal in their head but never actually checks to see if there's any food in the fridge. On the flip side, an act-only model is like a chef frantically running around the kitchen, throwing random items, maybe an onion, maybe a shoe, into a pot without any recipe or plan at all.
And that brings us to the core innovation of the paper, ReACT. ReACT is a paradigm that generates both reasoning traces and task-specific actions in an interleaved manner. It is literally the evolutionary synthesis of those two isolated paradigms we just talked about. By prompting the model to produce free-form thoughts right alongside domain-specific actions, it can finally perform dynamic reasoning. It's actively adjusting its high-level plans while it's in the middle of acting. When you actually put this into practice, it builds into this powerful, continuous loop flowing in two directions. First, we have reason to act. The model uses its reasoning traces to induce action plans, track its progress, and handle any weird exceptions. But equally important is act to reason. The model takes actions, like querying Wikipedia API, to gather actual real-world facts, and then feeds those observations right back into its context window. This creates an unbroken loop. Reason, act, observe, reason. The AI's thoughts guide its actions, and the real-world results of those actions update the AI's thoughts.
Of course, theory is great, but does this actually work? Well, the researchers put ReACT to the test on some seriously knowledge-intensive tasks. Specifically, HotpotQA, which requires complex multi-hop question answering, and a fact verification benchmark called Fever. The catch? The model isn't just handed the answers. It has to actively retrieve knowledge by interacting with a simple Wikipedia web API using specific actions like search, lookup, and finish.
Looking at the empirical data from these tests is just fascinating. It visually proves that ReACT consistently outperforms baseline models that rely on acting alone. But what's the absolute best approach? It's actually a hybrid. The data shows that combining ReACT with a chain-of-thought self-consistency model yields the absolute highest performance across different sample sizes. You're getting the strict logical structuring of chain-of-thought seamlessly combined with the grounded information retrieval of ReACT.
To really understand why that combination is so incredibly powerful, we just have to look at the failure modes. This highlights exactly what's at stake here. A standard reason-only model fails due to hallucination a staggering 56% of the time. It just makes things up because it literally can't check the real world. ReACT, on the other hand, drops hallucinated reasoning failures to literally 0% in this sample, because every single thought is grounded in a real Wikipedia observation. However, in the spirit of full transparency, ReACT does have a higher reasoning error rate, 47% compared to 16%, often because if a search comes back empty, the model can get derailed and struggle to break out of a repetitive loop.
Because of this exact trade-off between factuality and flexibility, the researchers detailed a brilliant hybrid strategy. They basically allow the model to seamlessly fall back between the two modes based on heuristics. If its internal knowledge isn't confident in an answer, boom, it automatically triggers React to search the real world. Conversely, if React struggles to find external facts within a certain number of steps, it just falls back to the model's internal knowledge using chain of thought. It's super elegant.
So we know React is incredibly good at retrieving facts. But what happens when we shift gears to something way more complex, like interactive decision-making? To find out, the researchers tested this in two massive simulated environments. First, AlfWorld, a text-based game where the agent navigates a household to achieve goals. And second, WebShop, a simulated online store with over 1 million real-world products where the AI has to buy exactly what a user asked for.
The results here completely blew me away. In the AlfWorld environment, React achieved a massive 34% absolute jump in success rate over state-of-the-art imitation learning methods. 34%. Just by giving the model the ability to interleave sparse reasoning thoughts with its actions, it vastly outperformed agents that had been trained on 100,000 expert trajectories. So why does this make such a huge difference? Because the AI is no longer just clicking aimlessly based on pattern recognition. In AlfWorld, React uses reasoning to inject common sense. It actively deduces that, hey, a desk lamp is probably on a desk, not in a fridge, before it even starts searching. In WebShop, it explicitly reasons about a product description before clicking buy, bridging the gap between a noisy, messy web page and the user's specific constraints. And compared to prior work, React's flexible reasoning avoids those dreaded endless loops because it can actually decompose massive high-level goals into smaller, manageable sub-goals. This highly transparent reasoning process leads to what is probably my favorite feature, true human-in-the-loop interaction. Because the model's plan is written out in plain language, you can see exactly why it's about to make a mistake. If you spot it hallucinating, you can literally just manually edit that single sentence in the thought trace. Instantly, the AI absorbs the correction, shifts its action plan, and completes the task. There's no reprogramming required at all. You just correct its thought.
And that is absolutely the most crucial takeaway from this research. As the authors state, combining reasoning and acting contributes to model interpretability, trustworthiness, and diagnosability across the board. We are finally moving past those frustrating black box systems that we just have to blindly trust. With React, we can clearly see the why behind the AI's actions and naturally course-correct it when it strays.
So, this paper clearly proves that synergizing thinking and acting creates a fundamentally more capable, grounded system. But here is the crazy part. This was largely done with few-shot prompting on frozen models. So, I'll leave you with this final thought to chew on. What happens when we take this React paradigm, scale it way up with massive multitask training data, and then combine it with reinforcement learning? We may very well be looking at the foundational architecture for the ultimate generalist AI of the future.